Assalamualaikum warahmatullahi wabarakatuh. Good day, everyone. Here we are presenting our article entitled Silicone for Lithium Battery Anode Derived from Geothermal Silica through Magnesiothermic Reduction and Double Stages in Acid Leaching. On behalf of all authors, I am Fabio Delanta will bring this article on the webinar of ICESTA 2021. Okay, this is the presentation outline we are going to give. First, an introduction discusses this research background and purpose, and the second is the materials and method applied in this research. Third, there is an explanation of the research results and ends with conclusions and acknowledgement. In the extraction and processing of geothermal energy into electricity, suspension waste is produced. This suspension contains dissolved plenty kinds of heavy metal such as iron, dissolved manganese, mercury, selenium, zinc, and silica. In a geothermal power plant, slurry can be produced up to 10 tons per day, from which approximately 10% solid is produced and majorly consists of silica. Silica is used for various purposes over many fields such as glass coating, aerogel silica, superhydrophilic coating, aerogel silica, absorption of organic compounds, silica gel in food industry, sensors, packaging, carrier media, and mesoporous silica, cement mixture, and environmentally friendly precursors. Silica can also be formed into silicon as a material in electronic equipment, photovoltaic cells, and anode for lithium batteries, solar grade, and semiconductor materials. The prospect of silica as a material for energy storage at present is very appealing. Nevertheless, this innovation requires that silica should be converted into silicon to provide function as energy storage anode. Silicon has a high potential capacity. The capacity of silicon anodes is almost 10 times higher than the conventional graphite anodes. Silicon has been reported that shows a high storage capacity, which is 4,200 milliampere hour per gram. Also, it is cheap and safe. Silicon anodes have large volumetric and gravimetric capacities. Thus, it can be reasonably utilized for anode component in lithium batteries, bestowing its potential to replace graphite anodes. The modification of purification process and best condition for magnesiothermic reduction of geothermal silica, as well as the use of silicon as a lithium battery anode, have not yet been comprehensively studied. Therefore, it needs to be further investigated. The objective of this research were, first, to investigate the best magnesium and silica ratio that can generate the best silicon yield and silicon conversion to silicon through magnesiothermic reduction, to assess the best acetic acid concentration on silicon purification by XRF and XRD analysis, and to evaluate the best silicon and graphite mixture composition as lithium battery anode by testing the battery performance using the battery system test BST-8 analyzer. Now we move to the methodology of the research. Firstly, the materials used to run the experiment including geothermal silica as the silica source, magnesium powder, sulfuric acid, demineralized water, and etc. Generally, the experimental steps are as follows. First, purification treatment of geothermal silica, magnesiothermic reduction process, purification of synthesized silicone, the silicon yield and conversion calculation, and preparation and performance test of lithium battery anode composite. The complete assembled battery composites were tested for the charge-discharge value using a battery system test 8 BST-8 analyzer. And this is the results and discussion. First, characterizations of purified silica from geothermal silica and the effects of purification treatments. XRF results reveal the effect of purification steps upon the geothermal silica. It can be seen that after solder process, the purity of silica increased from 85% to 96%. The XRD analysis results showing that the significant differences can be observed, that the recorded metal oxide peaks were significantly reduced, leaving some tiny peaks of metal oxides. Therefore, the purification treatment through the acid leaching and solder process were successfully removed the metal oxides impurities and produced high purity of silica as the main material in silicon preparation. Next result, the effect of ratio of magnesium and silica on yield of silicon in magnesiothermic reduction process. The effect of magnesium and silica molar ratio on the yield of silicon from the reduction process and the conversion of silica to silicon. The observed magnesium and silica ratio that produced the highest yield of silicon and the conversion of silica to silicon was 2:1. XRD pattern of the product of magnesiothermic reduction with different ratios of magnesium and silica. This signifies that the magnesiothermic reduction treatments were successfully converted silica to silicon. As discussed earlier, the best molar ratio that generated the highest composition of silicon was by applying magnesium and silica ratio of 2:1. And then the effect of purification treatment to the product of magnesiothermic reduction. The effect of acetic acid concentration on yield of silicon in the second acid leaching treatment. Based on this result, the best acetic acid concentration was by applied for mixing with hydrofluoric acid in second stage acid leaching treatment with the highest concentration of silicon was achieved by applying 25% of acetic acid. Summary of the effect of several treatments. It can be concluded that the purification treatment applied to remove the impurities from the silicon product was successful with final silicon purity of 98%, showing its potential to be used as lithium battery anode material. Effect of silicon and graphite ratios and number of cycles tested on lithium battery anode performance. The figures show the results of battery tests in the form of specific capacity of 12 cycles. The best silicon and graphite ratio to maintain the capacity after went through the cycle was 10/90. It can maintain the specific capacity around 2 to 5 mAh per gram at the 9th cycle test. The study focused on the utilization of geothermal silica as the silica source to synthesize silicon as the lithium battery anode component. Silicon conversion was performed using magnesiothermic reduction process at 650 degrees C for 7 hours. The best yield of silicon and conversion of silica to silicon were 26.46% for the yield and 85.6% for the conversion by using 2:1 magnesium and silica ratio. In the purification treatment, it was found that the acid leaching achieved silicon yield of 29.45% with silicon purity of 58.9% for the first step using hydrochloric acid, and silicon yield of 25.97% with silicon purity of 98% for the second step using a mixture of hydrofluoric acid and 25% of acetic acid. The best battery performance in terms of specific capacity was found by applying silicon and graphite ratio of 100/0 with the value of the first cycle of 358.5 mAh per gram. These findings present the reliability and feasibility of the geothermal silica and acid leaching treatment to generate the high quality of silicon for lithium battery anode component. That's all our presentation for today. Thank you very much.